Okay, welcome to the Millennium Falcon. We're going to talk a little bit more about specifically TCP in this guy. Right? So TCP packets and UDP packets in detail, as opposed to just the overview. All right, so TCP, hopefully you remember, Transmission Control Protocol, right? Operates on the transport layer, so T for TCP and T for transport. That's the way it helps me remember it, right? And that's in the OSI model there, okay? So big thing, reliable data delivery. Okay, how does it do that? So just to refresh your memory, these first three layers, we're dealing with data, all right? TCP, the transport layer, is the first time we add on a header to our data, all right? So first three layers, it's simply the processing the data that we're actually dealing with in the transport layer. Now we're starting to get ready to prepare it for transportation across the network. Couple protocols, or I don't want to say it, applications, protocols that exist on the TCP layer, Telnet and SSH. We're going to deal with those when we talk about, come on you, when we talk about remote into a router. We'll also look at FTP and its brothers and sisters, secure FTP and secure copy protocol. Right? Those are all files or file exchange protocols. This guy's all mail, right? Simple mail transfer protocol, post office protocol, and internet messaging is a protocol. Right? Hey, acronyms. What are you going to do? HTTP, that's web, and border router, right? Border gateway protocol, right? So those are all different protocols under the TCP protocol. So there's a whole bunch. It's like I said, TCP IP is a suite of protocols. Okay, so how does it do that whole secure message transfer? For three reasons. Let me find my pen here. There it is. It's connection oriented, means there's an established connection between the sender and the receiver. There's sequencing and checksums. The data comes in a particular sequence, it's numbered. Checksums say, hey, if the checksum value doesn't mathematically work out to be what it should, based upon the data you received, then there was corruption somewhere. And flow control. Hey, I'm only going to send you so much data. This is a guaranteed rate at which we're transferring. Okay. The TCP segment, remember, right? We're now dealing with segments or datagrams. Datagrams are for UDP, which we'll talk about in a little bit. So segments, the package of data that we're transmitting. So what that segment is made up of is whatever the upper data layer is. Now, what that means is your actual data, because the first 5, 6, and 7 layers, 5, 6, and 7, right? Those first layers are just the data. Transport layer adds on the TCP header. So it's the TCP header plus the data. That's where we're at. It's encapsulated, right? It's encapsulated, it encapsulates the data underneath its header, and then when you get to the network layer, the IP header encapsulates all the TCP stuff, right? So it's the Russian stacking dolls, right? The data is the inside doll. Then we place that doll inside the TCP header, and then we place that doll inside the IP header, the network layer header, right? So the TCP doll becomes the data for the IP packet, right? Segment versus packet, okay? So here's an example of a TCP layer, TCP header, excuse me, right? These are the bits from 0 all the way up to 31. So 32 bits total, right? Bit number 0 to bit number 31. So 32 bits total. And they're broken up so that different pieces of information come at different bits. Now we show it as being stacked, right? We go all the way down to our data. But think about this. This is just a series of pulses. It would be more correct to write this source port, destination port, sequence number, acknowledgement, all going across. Why? Because they're coming through a single wire in a form of zeros and ones, right? That's all we would see if we could watch the information go through. We just see or hear or listen to, receive a series of pulses, right? Whether that be RF pulses, light pulses, or charge. That's all we'd see. So even though we're depicting this as being a stack, and it'll often referred to as the TCP header stack because you stack it on top, it's really just a stream, right? So when we're looking at those, at these charts, think of it as, from 0 to 16, with the first 16 bits, the first 16 bits is reserved for the source port. You read that number, translate it into a decimal value, and that's the source port. The next 16 bits, that's the destination port. So read those zeros and ones, transfer it into a numerical value, that's the destination port. The next 32 bits are the sequence number. Translate that into a decimal value, that's what number in the sequence it is, and so on and so on and so on, all right? Acknowledgement is also a sequence number as well. It's kind of the same thing, but it's don't quote me, it's later on in the slide, the previous sequence number. All right, here's what all those boxes mean. Now, I'll let you pause here and view this slide and read through it, and I urge you to read through it, right? Take a look at these definitions. It's the chart just spelled out. So it's the previous table just spelled out for you, verbosely, saying here's what everything is. Couple things to bear in mind. The header length is variable. Minimum of 20 bytes, maximum of 60 bytes. A couple of things we're going to see a lot of coming up soon. The ACK and the SYN or the sync, right? The sync ACK. That's the three stage handshake we're going to be talking about. Padding. We want to ensure that the TCP header is a multiple of 32 bits. Right? We gave ourselves 0 to 31. TCP headers have to be a multiple of those 32 bits. So if they're not, then we leave some zeros there for padding, right? And then finally, the data. That's your HTTP web page, right? So take a pause, look over these details. It's also in the slides only PDF. So make sure you understand what's going on there. Here's the three-way handshake I was talking about. Sync, ACK, and ACK. Now, those aren't just words. Those are flags. They are contained in the flags part of the TCP header. They represent specific bits that are turned on or off, 0 or 1. When we do a Wireshark activity, we're going to look at that acknowledgement, that three-way handshake, and actually view the flags and see the bits being turned on and off, right? Not so much in real time, but sequentially, right? So only after that three-way handshake is the payload or data sent. Are you sure I'm connected? Are you who you say you are? You're the right recipient? And do you acknowledge that I'm the right sender? You're talking to more than one person at once. I want to make sure you know I'm me. Then after that is established, then the payload or data is sent, right? Now bear in mind, the TCP payload is just the data, right? Sequence numbers are increased. That's why they're sequence numbers. And the acknowledgement number confirms the correct length of the message was received, right? So sequence and acknowledgement numbers are closely related. You'll see one turn into the other. And there's just a pictorial representation of a three-way handshake. We have computer A on the left, computer B on the right, and here's what you might actually see. So sequence number, becomes the acknowledgement number for, the sequence number for A becomes the acknowledgement number when B sends it back. Follow? The sequence number for B becomes the acknowledgement number for A when it sends it back. Okay? Saying, hey, your sequence number was this, I got that number, here's my sequence number, and it's allowing that handshake to confirm that the sequence or the previous message was received, right? So sequence and acknowledgement numbers, those big 32-bit numbers, are related to one another, okay? Anything else, Bear? Yeah, and bear in mind that sync and synac and ACK, those are the same bits used over and over again, right? Sync is turned on and ACK is turned off, and then down here sync and ACK are both turned on, and down here sync is turned off and ACK is turned on, right? So it's the same bits being turned on and off at different points in that handshake. And here it walks you through a typical, packet and TCP header, and then it describes what you're looking at in each of those, right? So even though this software, and this is an actual screenshot of Wireshark, even though this software is displaying 80, what's really coming through is a binary value, all 8 bits with the correct bits turned on or off, right? It's interpreting that and reserved in those 16 bits, it's actually 16, right? So those 16 bits are reserved to describe the port number, the source port number. The next 16, the destination port number. So if you looked at these, you'd actually see 16 bits, all lined up next to one another, turned on or off to sum up to 80. I'm not going to do that in my head because I only have 15 minutes for the video, right? Then, down the list it goes. This is what a Wireshark screenshot will look like. Right. Let me see here. Continuation of that, just to go with flags and acknowledgement, window size, checksum, and again, checksum, valid outcome. Did the data I received match what you sent me? Right. UDPs, again, on the transport layer. Sorry, I don't have a nice mnemonic to remember, but if you know that TCP stands in the transport layer, UDP is its sister, stays in the transport layer as well. More efficient. Why is it more efficient? Because it's not connection oriented. So when we look at the stack, you're going to see it's much, much smaller. Great for things that if data is lost, oh well, live with it. Video, audio. You ever get audio that skips? Video that gets pixelated? You hear the audio but the video freezes? That's UDP. Larger volume of data. Why? Because there's less header. More space for the data, much less space for the header. All right. Couple of the protocols that exist under UDP, DNS, right? Dynamic Name Services. Simple Network Messaging Protocol, syslog, NTP, that's time, right? WinS, it's a Windows networking protocol. RIP is a router protocol. All of those are UDP, connectionless, right? I don't care who you are. Somebody requested this DNS address. Here it is, right? We don't have to agree. If you don't need it, who cares, right? I don't need to know who you are in order to provide you an IP address. It's public knowledge. That's how it works, right? Timing protocol. You want the time? Sure. Here's the time. It's 5 o'clock. What do I care who you are? It's connectionless, right? Only 4 fields are contained in UDP. Source port, destination port, length, and checksum. Checksum's nice. Is the data I sent you the right data, right? So take a look at this. Oh, here also. Checksum field in UDP in IP4 is optional, required in IPv6. IPv6, a little bit different just from that point alone, right? Here's that stack I was talking about. Yeah, compare that to the TCP stack. Hit rewind a little. Yeah, much, much smaller. More room for data. Right? So that's TCP and UDP in a nutshell. Again, all these quick overviews. Hopefully you have lots of questions. So we're going to see some of this stuff in action in Wireshark. If you have any questions, you know where I am.